Right, let us continue from where we left off, but before that one point, determinant u of course can also be minus 1, but we do not consider that aspect because we want to retain the positivity of the integration volume. So, determinant u equal to minus 1 we ignore and we retain determinant u equal to 1. The net result is that when we look at the integration, the bilinear form in the exponential is unchanged by the rotation, and at the same time the integration volume is also remaining unchanged, integration element is also remaining unchanged. So, now the important thing is that A tilde is a matrix which is diagonal, and the diagonal elements represent its eigenvalues. Therefore, because it is a diagonal matrix, we can split this integral into D, into a product of D independent integrals, each of them containing one eigenvalue, and that is what it is displayed in this expression. Making use of the previous formula for one dimensional case, we apply that formula here and we end up with the expression here, where for each eigenvalue alpha I we get a factor of alpha I to the power 1 by 2 in the denominator. So, we have the product of 2 pi 1 by to the power 1 by 2 corresponding to each integral. So, there will be d factors of 2 pi to the power 1 by 2. So, that is 2 pi to the power d by 2, and in the denominator we will have a product of alpha 1, alpha 2, alpha 3 up to alpha d to the power 1 by 2. Now, the product of these eigenvalues in the denominator is nothing but the determinant of the matrix A. So, we can write this whole expression as 2 pi to the power d by 2 determinant A to the power minus 1 by 2, because it is in the denominator. Now, the important point, the integral will only exist if all the eigenvalues of the matrix are positive, and which will only happen if the matrix is positive definite. I mentioned earlier that the matrix A has to be real, symmetric and positive definite. Now, because it is symmetric, we can diagonalize it. Had it not been symmetric, we could not have diagonalized it, and had it not been positive definite, we would not have had this eigenvalues of the matrix in this form. We could not have put the integral in this form. So, that is where the relevance of these terms comes into play. Now, let us look at this. The log of determinant A. Now, the determinant of A is the product of the eigenvalues of A. Therefore, log of determinant A can be written as log of the product of eigenvalues of A, and that is equal to the sum, because when you take the log of a product, it translates to a sum. So, it becomes the sum of the eigenvalues of various eigenvalues alpha 1, alpha 2, alpha 3, log alpha 1 plus log alpha 2 plus log alpha 3 and so on. Now, recall A tilde is a diagonal matrix, all of whose elements, all the diagonal elements are the various eigenvalues. So, instead of alpha, I can instead of summing over alpha, I can use the trace, the expression of trace also. But the important thing is to note that because it is a diagonal matrix, the product of the eigenvalue is equal to the matrix, and if we have a function of the matrix A tilde, for example, we want to work out say log of A tilde, that will be equal to log of the various eigenvalues, and therefore, when I use sum the log of eigenvalues, in other words, log alpha I will also be a diagonal matrix with all the elements of the diagonal matrix being log alpha 1, log alpha 2, log alpha 3 and so on. Therefore, when I want to sum over all the log alpha i's, I can as well use the trace for the log alpha log of the matrix A tilde. In other words, what I get is log of determinant A is equal to trace log of A tilde. Substitute A tilde equal to its expression in terms of the rotation matrices and apply the cyclic relationship. We end up with this expression being equal to trace log of A. In other words, what have we established? We have established that log of determinant A is equal to trace log of A, and therefore, determinant A to the power minus 1 by 2 is nothing but exponential minus 1 by 2 trace log of A. We simply substitute this value in the expression that we had, and we arrive at the result. This integral I is equal to the 2 pi to the power d by 2 exponential minus 1 by 2 trace log of A. So, there is a lot of manipulation here, but it is a very important result, and it displays many important relationships in matrix algebra, which we have to use again and again. Please note this particular point, that if we have a diagonal matrix, for example, A is a diagonal matrix, then log of A will also be a diagonal matrix, and its elements will precisely be the log of those diagonal elements which constitute the matrix A. And if we are, for example, if we are looking at the matrix A squared, then again we will have a diagonal matrix whose elements are squared, alpha 1 square, alpha square, and so on. So, that is the property that we have made use here. Right. We now look at property 2. Now, property 2 is again, let us first look at the one dimensional case, and then we will generalize. Generalization is in this case is very elementary. We need to evaluate this integral. Let us call this integral I. It is simply, in fact, we have done this earlier in the context of determining or calculating the movement generating function of the normal distribution. Dy is equal to exponential minus this. We convert this to a square, a perfect square involving the terms y and 2 ry, and an extra piece which is independent of y is taken out. So, we write this a y square into 2 r a y square minus 2 r y as a into y minus r by a whole square minus 1 by a r square. Now, look at this carefully. This factor 1 by a r square is independent of y, and therefore, it can be taken outside the integral. And what are we left with? We are left with the expression integral dy exponential minus 1 by 2 a y minus r by a whole square. Recall, this is of the same pattern, same form as the PDF of a normal distribution. And what is the coefficient of y in this case? The coefficient of y in this case is a, sorry, y square is a. The coefficient of y square is a, and when you simplify this expression, just as we did in the one dimensional case, this particular portion when integrated gives you 2 pi upon a to the power 1 by 2, and this part exponential minus 1 by a minus minus becomes plus, and we have 1 upon 2 a into r square. This goes outside the integration because it is independent of y, and we have this expression. Now, we generalize it to the matrix case. In the matrix case, in the d dimensional matrix case, you see what did we have here? We had here a y square minus 2 r y. Just keep track of this, a y square minus 2 r y on the left hand side. Now, let us look at this. A y square is written as y transpose a y, y transpose a y minus 2, we have introduced a new factor rho transpose corresponding to r over there into y. And this can be written as y minus a inverse rho transpose a y minus a inverse rho minus this expression. This is absolutely same as we did in the case of the one dimensional case when we completed one perfect square and we took out a term which was independent of integration and we took it outside the integral. That is precisely what is done here. And now what we do is simple substitution. We substitute y dash equal to y minus a inverse rho. Obviously dy is equal to dy dash, right. So that does not make any difference, and in terms of y dash we get this expression minus 1 by 2 y dash transpose a y dash plus rho transpose y dash. This is what we get, and when we substitute, when we make use of the earlier expression, we get this result. This is quite straightforward, there is not much ado about it. If you look at this, this correlates to what we had done earlier. What was there in the one dimensional case? It was 1 by 2 r square, I am sorry, it was 1 by 2 r square upon E, and that is precisely what it is matching here. We can have a look at that to confirm. Let us have a look at this. 1 by 2 a r square, precisely what I have written here, 1 by 2 a. So, this matches to this expression. This expression was taken outside the integral, and this we had done earlier in the context of the previous problem, previous example for a d-dimensional case. So, this part is done. This part is the extra piece that we have, which we took outside the integral, and we get this result. This integration gives you this part, and this part goes out as this part. Then we have another property, another very interesting property is this particular property is slightly more involved, but it is very important and we need to look at it. You see, what we do here is, you see, if you look at this, these are factors which are related to this y over here, various expressions which are extracted out of this column vectors y and y transpose, which are extracted and put as part of the integral. So, here what we do is, let us start with this matrix. Now, if you look at this, if I take the instead of this matrix, I take a new matrix, I take this matrix expression. For the moment, just forget about this, forget these quantities, right. What I do is, instead of this matrix, this particular exponential, I write this exponential, and then what I do is, I take the derivative of this whole thing including the integral with respect to del rho k 1. Now, what will it do? When this del rho d of d rho k 1 operates on this, it gives you this integral again, and then it integrates this exponent, and when it is when this it differentiates this exponent, and when it differentiates this exponent, it pulls out that particular quantity which is related to this, which is and what is the coefficient of rho k 1? If you look at this in this particular expression, the coefficient of rho k 1 will be nothing but y k 1 from this expression, from this particular quantity. So, instead of writing y k 1 here, what I have done is, I have introduced an additional factor in it later it will be called the source term, but for the moment you can use it an additional quantity, additional factor that I have introduced here in the integral, and then when I differentiate this, because there is no rho here, there is no rho in this quantity, there is only a rho over here, and when I use this rho in this quantity, I pull out the corresponding y. The rest of the rows, because they are not this row, will become 0, and the net result would be that I would precisely get this expression when I differentiate with respect to rho k 1, rho k 2, rho k 3, rho k n. When I do all this differentiation, every case I will get one factor. When I differentiate with respect to rho k 1, I will pull in y 1, y k 1. When I differentiate with respect to rho k 2, I will pull on y k2 and so on. So, if I differentiate with respect to all these quantities, then I will get this factor. In other words, these two quantities are equivalent. And therefore, now we have done this differentiation already. We have done this differentiation already, but at the end of the day we need to throw out this row. So, after doing this differentiation, remember, after doing this differentiation, the result that I get, in that result I will put rho equal to 0, and then when I put rho equal to 0, this expression will go away, and when this expression goes away, I recover this. I have pulled back factors of this due to the differentiation, and I get precisely this quantity. In other words, what is it? First of all, add the source term. Step 2, differentiate with respect to rho k1, rho k2 and so on. Step 3, after differentiating, put rho equal to 0 and you get the same quantity as this one. Now, we know the integral of this expression. The integral of this expression is just now done, and that is precisely this. This is the integral of this expression. Therefore, this integral is nothing but this integral or this expression differentiated with respect to rho k1, rho k2, rho kn, and then rho put equal to 0, and then rho put equal to 0. Now, again this factor is independent of rho. Let us take it to the other side. Let us take it outside the differentiation operators. You put 2 pi d by 2 constant, you take this which is independent rho outside, and this differentiation operators which are differentiation with respect to rows, various rows are operating on this quantity. Now, let us look at what happens. Let us take the first case. Let us differentiate with respect to one row, rho k. Now, when you differentiate with respect to one row and use this representation of the matrix, this is precisely what you get. Summation j equal to 1 to d 1 by 2, and then you get these two expressions, which can be written compactly as this particular expression. But remember, then I have to put, therefore, what do I get? I get this expression is equal to this expression, and this expression turns out to be differentiation of this, and when I do this differentiation I get this expression. Now, when I put rho equal to 0, this term vanishes. When this term vanishes, the whole thing vanishes and I end up with 0. So, therefore, if I have one factor here k1, the whole integral gives me 0. To reiterate, if I have one factor here, the whole expression will turn out to be 0, and indeed if you have an odd number of y k's here, the net result will always be 0. Let us look at an even number. Let us look at two differentials, rho k1, rho k2. Rho k1 result we already have with us. So, we differentiate this again with respect to rho k2. Now, when you differentiate this with respect to rho k2, what do I get? I get an expression similar to the previous case with respect to k1, and I get the expression with respect to k2. When this is differentiated with respect to k1, I get this. When this is differentiated with respect to k2, I get this. But when this is differentiated with respect to k2, I get these coefficients. Now, these coefficients are independent of rho. Please note this point. These coefficients are independent of rho. Therefore, when you put rho equal to 0, what happens? These coefficients survive. This rho equal to 0 gives me 1 because it is in the exponent. So, the exponent being 0, this gives me 1. These become 0, and this particular term, the A inverse k1 k2 survives. So, the net result is, let us see, when you have two differentiations, two terms in the integral y k1 and y 2, then what we have in the end of all this manipulation, we have at the end of all this manipulation is A inverse k1 k2 plus this thing plus this, and when you put rho equal to 0, this becomes 1, the exponential becomes 1, this becomes 0, this becomes 0 and this is retained because this is independent of rho. So, what we get is 2 pi to the power d exponential minus 1 by 2 trace log this thing and A inverse k 1 k 2. So, this is for two quantity, two y's, y k 1 y k 2 appearing in the integral, y k 1 y k 2 appearing in the integral. Now, as the number of values y k 1 y k 2 k 1 k 2 k 3, the number of differentiation increases, the exponential factor is multiplied by polynomials in row of the order n. Now, what does it consist of? It consists of either even or odd powers. Now, 1/0th power term remains, 1/0th power term remains, which will survive in the case when the limit rho equal to 0, rho tends to 0 is taken. And however, that 0th that term which survives will consist of n by 2 factors of this type. K 1, K 2, K 1, K 3, K 1, K 4, K 1, K n, K 2, K 3, K 2, K 4 and so on, K 2, K n and so on. But remember, this is symmetric, K 1, K 2 is same as K 2, K 1. So, the net result is you get n by 2 terms which survive when there are n terms y k 1, y k 2, y k n in the integral sign. So, that this integral is very important. For odd numbers it gives you a 0 result, for even numbers it gives you a number of terms, n by 2 terms in fact, where n is the number of k 1, k 2, k n. You can have a look at this, it is given, yeah, here it is. Yes, A inverse k 1 k 2, A inverse k n minus 1 k n plus the permutations of these quantities, there will be n by 2 terms in total. Now, we come to, so that is about Gaussian integrals. These three formula were very important, they find a lot of applications. Now, we come to another beautiful theorem in statistics, which again has a lot of applications, which is called the central limit theorem. What it says is, suppose x 1, x 2, x 3, x n, they are identical, independent, identically distributed random variables. Independent, x 1, x 2, x 3 all are independent and they are identically distributed random variables. They have a finite mean and a finite variance. The mean of each of them is mu and the variance of each of them is sigma square. Then the following expression z n limit n tending to infinity sigma x I, that is the sum of all the random variables, minus n mu upon under root n sigma square tends to the standard normal distribution, standard normal distribution. This is a very important theorem. Let us look at it in more detail. What is the important part in it? The important part in it is the variables x 1, x 2, x 3 etc. are independent, identically distributed, but how are they distributed, that is irrelevant. In other words, the nature of the underlying distribution of x 1, x 2, x 3 is not relevant. Howsoever they may be distributed, they may be uniformly distributed, they may be normal distributed, they may be binomially distributed, Poisson distributed, whatever, in any distribution they are, provided all these variables are distributed similarly and they have the same mean and variance and they are independent, then this condition automatically holds. That is the beauty of this theorem. The beauty of this theorem is that it does not bother, it does not worry about the underlying distribution of the variables. It does not say that it must be a Gaussian distribution, it does not say that it must be a uniform distribution, it holds for all distributions. Right, let us look at the proof quickly. Let us assume that there are n statistically independent and identically distributed random variables x 1, x 2, x n. Let us assume that p x is the probability density function of x, and that is the it is a function of x 1, x 2, x n naturally, and because they are independent, p x 1, x 2, x 3 can be expressed as p x 1, p x 2, p x 3, p x n, because they are independent. Now, for simplicity, let us assume that E of x I, that is the mean of all these random variables, is 0. It's simply a shifting of the origin, and we also assume that sigma square is equal to E x I square minus E y, because this quantity is 0, this quantity is 0, therefore, we can write E of x I square is equal to sigma square. Because the mean is 0. So, the second movement about the mean and the second movement of the about the origin do coincide, and we write it as sigma square. Now, we need to calculate the distribution of z n, where z n is equal to 1 upon root n sigma x I. Remember, the mean is 0, the variance is sigma square. Let us work out the parameters of z n. Mean of z n is equal to mean of this expression. When you simplify this expression, expectation of this, you can take this expectation inside this root n, because this is deterministic. Again, because the expectation of a sum is the sum of the expectations, you can take it here, and each of them has the expectation of 0. So, the whole thing has the expectation of 0, therefore, E of z n has an expectation of 0. Similarly, E of z n square, when you work it out, and this part is straightforward, this part is straightforward. Now, because they are independent, what do we have? We have E x y is equal to E of x, E of y, and making use of this, we can write this as E summation x y is equal to summation E x x square plus y x 1 square plus x 2 square plus x 3 square plus x 1 E of x 1 x 2, which can be written as E x 1 E x 2, and using this we find that the summation of this whole expression is equal to sigma square. But E of x is equal to, please note, E of x is 0, E of y is also 0. So, in this case E x y, the cross terms, all the cross terms vanish, right, and we have E of x I square is equal to sigma square. Now, let us look at the probability density function of the of z. We define P and z as just as we did in the example to start this lecture. We want to work out P and z is what? It is the probability of the variable z taking a particular value small z. Now, because the variable z is has a number of variables, is the sum of a number of variables, which is represented by the sum z n, which is represented by the sum z n. Therefore, we must have we can take all these numbers, all these variables, the probability of all these variables which combine to which are present to give you the value z, provided that condition of summability holds. In other words, provided that z n is equal to z, where z n is given by summation, z n is given by what? Z n is given by the summation. Which summation? Z n is given by this summation, z n is given by this summation. So, provided that this summation holds, this constraint holds, you can have any values of x 1, you can have any values of x 2, x 3, x 4, x 5, whatever, but this condition must be met, that z must be equal to z n, where z n is defined by this. And how do we impose this constraint? Again we go back to Dirac's delta function. We impose this by setting this delta function over here. So, P and x, P and z is equal to integral d n p x. This is p x is the collective distribution of all the variables x p x 1, p x 2, p x 3, as you shall see just now. Now, the characteristic function is given by the Fourier transform of of p and z. Therefore, it is given by dz e to the power minus I k z p and z. Let us substitute this value of p and z in the correct expression for the characteristic function. We get dz e to the power minus I k z, and this whole expression comes as it is. When you do this integral simply over the delta function, z gets replaced by zn. So, this is what I have. Now, I substitute zn in terms of that particular expression that I mentioned earlier, this expression. So, when I do the substitution, I get this expression. Now, what I do is this x I e to the power minus I k 1 upon root n x 1 I take with this integral, minus I k 1 upon root n x 2 I take with the second integral, and so on. So, each integral has a factor of e to the power minus I k 1 upon root n with its appropriate x I with dxi with xi. So, they are all integrals which are identical, and therefore, I can write this expression as integral dxi pxi. This is dxi, this is pxi, and then this xi expression e to the power minus I k xi upon root n to the power n. And if you look at this carefully, and this is nothing but the characteristic function of k upon root n. In other words, what have we established? We have established that g n k, that is the characteristic function that we wanted or we started with, is equal to g k upon root n to the power n. This is simply algebraic manipulation, and therefore, this is what we have, g n k is equal to g k upon root n to the power n. Now, you can expand the right hand side as a Taylor series. If you expand the right hand side as a Taylor series and use the movement generating property of the characteristic function, the first movement, remember we have taken the mean as 0. So, the first movement, this expression becomes 0, and we have taken the second movement as sigma square as the second movement, and therefore, when you put these values here, you get 1, g dash k upon root n gives you 0, and this expression gives you minus sigma square, minus because we are dealing with characteristic function, we are not dealing with movement generating function. So, this to the power n gives me equal to g n k. So, a bit of simplification, what do we have? G n k is equal to 1 minus 1 by 2 k square upon n into sigma square to the power n. Take the limit as n tends to infinity, you get this expression. Remember, this is the Fourier transform. This is not the PDF itself, the Fourier transform of the PDF, but because the Fourier transform of a Gaussian is a Gaussian, therefore, it follows that because this is a Gaussian and this is, you can look at it carefully, it is simply a Gaussian unnormalized Gaussian expression, PDF unnormalized, but because it is Gaussian, it follows that the Px that it will correspond to is also Gaussian. That can be seen as I will show you in the next slide. Right. So, P n of z now we invert the Fourier transform, then we have P n of z is equal to exponential minus I k z g n k d k. Simply substitute the value of g n k which we had here. This is my expression of g n k, this is the characteristic function, this is the Fourier transform of p x. So, I substitute that Fourier transform of p x to x to invert the Fourier transform. This is the inversion of the Fourier transform, that is the inversion of the characteristic function, which is this, and when you simplify this as we have been doing throughout this lecture, you get this particular expression. So, it follows now that the PDF of z that we have obtained is nothing but the normal distribution PDF 1 upon under root 2 pi minus z square upon 2 sigma square, which is nothing but n 0 comma sigma square. Right, thank you.